We take up today on what I thought was our last lesson, but actually isn't going to be. There's going to be one teeny piece coming next. We take up the issue of partial fractions, and you're going to go, what on earth are we doing? She's got a rational expression on the board. What on earth can this have to do with matrices? Well, later on in a problem, matrices are going to solve it for us. But first, I have to convince you what on earth a partial fraction is. What you're looking at are two partial fractions. When added together, they make one whole fraction. Okay, we already know how to add them together, and we're going to do that. Of course, we know that to add them together, we have to make a common denominator, which would be our handy-dandy x minus 4 and x plus 9. So this part is not going to be new to you, but I need to prove a point. So, of course, to do the first fraction, it is missing the x plus 9, so of course we are going to multiply it by x plus 9, and that's going to give us a nice little 7x plus 63. If I do the same thing for the other fraction, it's missing the x minus 4, so I'm going to multiply it by x minus 4, and I am up to then 2x minus 8. At long last then, I add those together. Numerators are going to add up to 9x plus 55, and the denominator is going to make x minus 4 times x plus 9. And you have added those two fractions together. Been doing that since Algebra 2. Okay, now, what partial fractions are when you do this in reverse. Now I'm going to prove to you that this method works. We are going to take the fraction we just created, the 9x plus 55, over x minus 4 times x plus 9, and we are going to turn it back into the original fractions that added together to make this fraction. Now, this method only works if it's what's called a proper fraction, meaning the power in the numerator is less than the power in the denominator. Okay, so in this case, the highest power in the numerator is x to the first, and the denominator, if those were full together, it would be x squared. So that's going to work since the denominator has the higher power. Okay, so pretending we didn't know what we just did above, when you set up a partial fraction, you go, okay, if the common denominator is x minus 4 and x plus 9, then I know I had to have originally had fractions that had those two quantities in their denominator. Your question is figuring out what their numerators were. Okay, there's a system for doing this, and I'll make more sense of this after we finish this problem. If your denominator has x to the first, your numerator will have terms which begin with one power less than that. So what's left less than x to the first? Well, x to the 0 power, or in other words, a constant number. So therefore, in this problem, we know the numerator had to be just a number. It had to be one power less. Same way over here, that's x to the first, so it'll have to have been just a single number. You have to use a different letter to represent each possible term you can have. Okay, now we are going to solve this problem. And by doing that, we're going to treat it like it was a rational equation that you're solving. How do we solve rational equations? Well, we get rid of the fractions by multiplying by the common denominator. So that's exactly what we're going to do here. We're going to take this entire thing times the common denominator. Now, for once in your lives, I'm actually going to say this to you, and I know this is going to be a shocker, but do not put your brain in gear. Do not try to be creative. The common denominator is what's in the original problem. That has to be the common denominator. So do not try to figure out a common denominator. You're multiplying by the original denominator without fail. So I am taking this times x minus 4 and x plus 9. That's the denominator I was given in the first place. Okay, consequently, what's it going to do every time to this part on the left side? Sure, it's going to cancel. It should. It had the common denominator. So all you have left then on the left side is 9x plus 55. Okay, I'm going to do this slowly and carefully. I am taking the second fraction times x minus 4 and x plus 9. What is going to cancel? The x minus 4. So what is going to be left? Okay, and I'm begging, pleading with you. On this one, it's going to seem too simple. Why is she doing this? But on others, it's going to be more complicated. Please just write down what's left. Don't attempt to distribute and multiply right now. Just write down what's left. Okay, on B, same thing. I'm multiplying by x minus 4 and x plus 9. What's going to cancel? The x plus 9. And we're going to be left with the b and the x minus 4. So now, your goal is to solve for a and b. And you're going, how can I solve for a and b when I also have x's? That's 3 variables in one problem. You can't solve it. But there's sneaky algebra yet to come. So we do need to distribute the a and the b now. And on this one, yes, it would have been simple to do it earlier. On others, it won't. So I'll have ax plus 9a. I'll have bx minus 4b. Okay. This is where it goes weird. You're going, how can I solve for a and b when I got all these terms? This isn't going to work. What you're going to do is what we're at is for the a's and b's, the coefficients. We really don't care about the x's. The x's aren't having any impact here. So what you're going to do is you're going to make a system of equations. Yes, I said it, a system of equations. And you're going to solve that system. And to do that, you're going to go find, in this case, all the terms that have an x term, which I just highlighted there. And so you're going to turn that into equation using the coefficients only. You're not going to keep the variables. So you're just going to say 9 then has to equal a plus b, because those x terms on the right have to add up to be 9x. But we don't need the x's, we just need the coefficients. Okay, then you're going to go do the same thing with the 55, and you're going to do all the constant terms over here, which are 9a minus 4b. So now you're going to get a second equation that has 55 equals 9a minus 4b. And oh golly, look, it's a system of equations with 2 variables. Now, before we proceed, let me be sure I note that out here at the side. So we're going to say we're going to create a system of equations using terms with like powers. Okay, now, how you solve that system of equations is up to you. This one would be super simple to eliminate. Me personally, I would probably eliminate it. But because we're in the matrix chapter, their whole purpose with it is, hey dude, you could solve this with an augmented matrix or with a matrix equation. Which, I admit, if it's anything that's going to be remotely challenging, matrix equation looks good too. So, your choice here, whether you solve it by hand, with elimination or substitution, or if you solve it with a matrix equation. I'm going to solve it with a matrix equation just because that's the area they're trying to emphasize here. So, and I will let you shortcut, because we need to be fast and efficient on these. The matrix, I'm going to pull the coefficients off the a's and b's, so I'm going to have a 1, a 1, a 9, and a negative 4. I know I'm going to take that times the inverse. And what are the 2 numbers I'm going to multiply it with? Yes, indeed. It's going to be a 9 and a 55. So you can go to your calculator and punch that in. I changed up this problem and forgot to solve it, so I'm now really quickly solving it in my head. Whoa. I'm not doing well solving it in my head. I wish I had a pause button here. really fast so that I could solve that out. I should be getting duh. Wow, okay. Not being very smart about this. Of course, we already know the answer to this problem. We should get 7 and 2 because we already knew the solution to this situation. So I should be getting an answer, duh, of 7 and 2 for this particular problem. But something is wrong because that's not going to solve out. Because that's going to be 60, yeah it is, 63. You might say, oh man, okay, you can tell I'm almost done. This is the 8th lesson of the day I've recorded, sorry. So yeah, it's going to be 7 and 2. Wow, I've really lost it. And so the key thing though at the end, people think when they get done that the 7 and the 2 is the answer. That is not the answer. The answer, the question you were asked to find is what were the original fractions. So now that you know A is 7 and B is 2, you need to put that back in the original equation we set up here. We had A over x minus 4, so now we know it was 7 over x minus 4 plus 2 over x plus 9. That's the actual original fractions that were used to create this equation. And of course, we knew that. Okay, now the key to setting up partial fraction problems is getting the problem set up right in the first place. The working it out, yeah, there's a fair amount of algebra to it, but it's just that. It's just steps of algebra. If you don't set it up right, the whole problem crashes and burns. So we're going to look at just how do you set it up. In the book, they call this setting up the templates. Okay, we just did one like this first one. Pretend it could be anything on the top. We don't care what was on the top, but if the denominator was x plus 3 and x plus 2, you would know then that you were doing fractions with x plus 3 and x plus 2. Now the question is, what do I put on top? Well, this is x to the first. What's one less power than x to the first? Yes, indeed. It's a constant number. This one's also x to the first, so I put a constant number. It's just like the problem we did. Okay, this should prove my point better, though. On this one, I have x squared plus 4, which would not factor, and x cubed plus 7, which also would not factor farther. This proves the point much better. Since the power is x squared, what's one power less than that? X to the first. So I'm going to have ax, but now here's the wrinkle. You have to have every power from there down to a constant number. So since this is x to the first, I would also have to have plus a constant number. So I would have plus b. Now let me take that one step farther. On the next one, the power is x cubed. So when I start this, I have to start with one power less, which is x squared. Now I've already used a and b in this problem, so this one would have to be c. Now you must keep going downward till you get to a constant number. So going downward a power, the next power would be x to the first, so I would have to have a dx, and then I would finally, at long last, get to a constant number of plus e. Now, I'm not going to give you one that's mean and nasty, but that helps you see the pattern of what's happening. Whatever power you start with, then you've got to have every power descending from there until you get to a constant number. Okay, those are also, though, still fairly nice to deal with. Okay, it's these last two that are going to drive you nuts. They drive everybody nuts. And perhaps maybe I should digress off to the side for the moment. If I told you that you were going to add a fraction and you had x minus 2 squared, 4 over x minus 2, plus 7 over x minus 2 to the first power, plus 8 over x minus 3. What would your common denominator be? Well, the question would be how many x minus 2's? One of them has 2 x minus 2's in it. One of them has only x minus 2 to the first. So do I do 3? And the answer is no. You do the most you see in one fraction. So since there are 2 here, I would keep 2. That's the most I see in one fraction. Then I also see an x minus 3. That would be my common denominator. Okay, this problem I have here is just exactly like that, except we're going backwards. When I see that I had x minus 5 squared, then yes, there had to be a fraction with an x minus 5 squared in it. But the hidden condition is, just like this example I just did you, there could have also been a fraction with an x minus 5 to the first power in it. So anytime you have a quantity with two of them, then you also have to say, well, there might have been one of them. Or then, of course, I also have to have my x minus 3. Now, how do I decide what goes on top? Well, that's another key thing. It's based on the power that's inside. That is x to the first inside, not the square. It just means there's two of them happening. So since it's x to the first on the inside, we are only going one less power, which is a constant. We're going with a. This one's also x to the first, so it's only going to have a single letter b. This is x to the first. It's only going to have a single letter c. But the key thing is, if you have multiples, squared, cubed, whatever, you have to have every power of x represented. Now, it may well turn out that b one might turn out to be 0. It may disappear. Okay, and finally the last one, the one that most missed of all. You're going, well, it's an x squared and x minus 5. I should be no big deal. I just do a fraction with those two things in it. Well, unfortunately, you would be wrong. Yep, they're both in there, but there's one more fraction that's also a possibility. By the way, you always put pluses in it. If it turns out, if it's a minus, the letters on top will solve out to be negative. So just always use pluses. All right, here's the wrinkle. If there's two of these, it's just like the quantity above it when I had x minus 5 squared. It's like saying I had x to the first happened twice. So therefore, if I had x squared, my common denominator could have also had plain x in it. Okay, now this is the part that's really going to get you. Since it's x squared, it is indeed like saying I had x to the first power happen twice. So consequently then, we only put a single letter on top. Basic, easy way to remember, if you have a single variable on the bottom, you have a single letter on top. This is a single variable on the bottom, it's to the first, so it's got a single letter on top. And then the x squared minus 5, that's a quantity. And so now I go one power less, which means I'd have to have cx, and then keep going down to a constant, which would be plus d. Okay, your first 5 problems on your assignment are simply to do this. You're not supposed to work the problem out, you're just supposed to practice setting them up. Because the key to this, and lots of frustration, is to set it up right in the first place. Okay, I'm going to break the video at this point and then come back and actually work a couple problems full length.